Okay, how do we do these problems? What kind of work was I looking for? On this one, this is the image. This is the pre-image because it says it transforms JKLM to rectangle NOPQ. So this is the image, and this was the original figure over here. So you take image divided by original figure. So the scale factor is 3. On this one right here, it says here's the scale factor. So you take the point 0, 2, and you multiply each one of those by a half. So it becomes 0, 1. Okay. So you're gonna do that for each one of these points, like 4, 6 times a half. Each one of those numbers is multiplied by a half. So 2, 3, right? You do the last one. Dilation centered at the origin 2, 6, and it becomes this point right over here. Well, this is the image. This is the pre-image over here. Okay, so you always take image. Please put this down as your corrections. Pre-image. Okay, so what kind of numbers do we have? 7/4. So 7/4 divided by 2. When you divide fractions, you multiply by the reciprocal of what you're dividing by. So I end up with 7/4. Okay. Oh, doggone it. I knew something was wrong there because I didn't remember that being the answer. This right here is 7. This is 7/4. And when you multiply by a half, it's going to become 7/8. My bad. I'm not making the video again. Sorry. I copied the wrong number there. So it's 7/4 divided by 2. So 7/4 times 1/2. All right. Next one, number 4. We're going from this figure to this figure. So this is the image over here, image. This is the original one right over here, pre-image. So we're always going to take image, put this down again, divided by pre-image. And what happens here? You get 1.6 divided by 8. All right, well, that's a little hard to tell what's going on there. So what if I multiply the numerator by 10? It becomes 16, and the denominator by 10, that becomes 80. Still a little difficult to see what's happening here. 4 goes into 16 4 times. 4 goes into 80 20 times. Oh, now I'm there. 4 goes into 4 1 time. 4 goes into 20 5 times. So my scale factor is 1/5. You could do this on Desmos, and I just don't have time to flip over to Desmos. And well, I'll do it. I'm going to do it. I take it back. So you get over here and you go Desmos, right? And you do something like 1.6 divided by 8. It comes out to be 0.2. Maybe you don't recognize that fraction as 1/5. So you hit this little fraction deal right here, and it changes that rational number into a ratio. And so that's how you do that on Desmos. Hey, this quadrilateral is similar to this quadrilateral over here. So that means that E corresponds with A, and B, and F corresponds with B, and so on and so on. So when it says F, well, what does F correspond to? B. So B is 75 degrees. Okay. What does H correspond to? Let me change colors here. H is the fourth letter. D is the fourth letter. This is the kind of work I was looking for. D is 105 degrees, so 105. Next group of problems. Fill in the blank. Because the dilation is a rigid motions, it preserves the angle measures. Okay, so angles. Let's see, angle measure I probably should put here. Okay. The blank can be used to prove that the triangles are similar. Well, if this is 36 degrees and this is 90, I've got 90 plus 36, that makes 126. That means that out of 180 degrees, I've used 126 degrees, there's 54 left. So if this is 54, see that? Angle equal to an angle, another angle equal to another angle. That means that we've got angle similarity postulate. So I was looking for people to find one of these other angles, like show me that you can see that this is 54 degrees. People that put this work down, man, well done. Number 7. This kid right here is 64 inches tall, which I said is 5 1/3 feet. Okay, because 4 inches out of 12, right? So 60 inches is 5 feet. Another 4 inches is 1/3 of a foot. So it's 5 1/3 feet. And we're looking for this over here. So I would go 5 1/3 over x is equal to 8 Now, how big, this is the part that really messed people up. How big is this entire side of the triangle? 24. 24 right there. So some people did this. They said, hey, look, I know the denominator is 3 times as big as the numerator. So what is 3 times 5 and a third? 5 and 1/3 times 3. Well, 3 times 5 is 15 plus 3 times 1/3 is 1. So I get 16. All right. Now you could cross multiply. You can use Desmos, all that jazz. You're going to get 16. The two triangles are similar. Explain the reasoning. Well, what I was looking for is people to set up a ratio. 3.6 over 6. Shoot, what does that reduce to? It's, again, a little hard to see. So I'm going to multiply that by 10, and I'm going to multiply this by 10, and then I'm going to reduce that. So 6 goes into here 6 times, 6 goes into there 10 times, 2 goes into here 3 times, goes into the bottom 5 times. So we got 3/5. Oh, look at this. The other side is 3/5. So check mark, they're in the same ratio. Okay, so I got a pair of sides and another pair of sides in the same ratio, and the included angle is equal to each other. So that's side, angle, side similarity. Okay, I need to see something like this. I liked what some people did. They put down, is 3/5 equal to 3.6 over 6? And let me erase this here, right here, so we can see that 3.6 again. So then they cross multiplied and they got 18 when you go 3 times 6. When you go 5 times 3.6, you get 18. So check mark, they have the same ratio. Number 9, which similarity postulate or theorem proves that the triangles are similar to each other? Well, I don't have this side over here. I don't know what IG is. It does start looking like side, angle, side, but since I don't have that, I got to step back and I got to look for something else. Then I noticed, hey, I got a couple vertical angles in here. Angle similarity is about the easiest thing to use. And it would have been awesome if you would have put down vertical angles. Okay, so see if you lost a point or two there because you didn't have some evidence that you're getting a pair of angles in there. All right, now last thing here. Well, it's not the last, second to last. We're looking for that segment right there. And an angle bisector is dividing this side up in the same ratio. So let's put a ratio down, 8 to x as 12 to 21. It's the craziest idea. I did a little proof in my video that works. And yeah, I don't know. You can go back and watch that if you want. Probably not going to. In all honesty. So how many times does 12 go into 168? It goes in one time, and then there'd be a remainder of 4. It goes into 16 one time. 48, it goes into there 4 times. So x is 14. All right, so I just did a little cross multiply. On the next one, which is the last one, man, a lot of people did really well here. X is corresponding to 7, so I'm going to go x over 7. I'm going to set that equal to 2 over 5. 2 over 5. Now, ratios are a little bit flexible. Like if you would not have seen that guy right there, you could switch the locations on those two. You could have 5 over 7 equals 2 over x. But that's not one of the options here, right? You could switch the locations on these two, and you could have x over 2 equals 7 over 5. What allows me to do that? Why can I switch them? Well, I'm still taking 2 times 7, and I'm getting 14, and I'm taking 5 times x, and I'm getting 5x. That's exactly what I'd be doing right here. 5x, 14, right? I divide by 5, and it goes into there 2.4 times. Hey, thanks for watching my video and doing all the corrections. I need you to try that assignment that I have on McGraw-Hill.